So, hey guys, this is Abhinav here, and today we're going to look at some interesting topics of organic chemistry and some which are related to organic chemistry but are very important for understanding some things in organic chemistry. So, first, we'll just brief through the physical properties of carbon. So, carbon has an atomic number of 6, that is 6 protons, and it has a mass number of 12, which is to 6 protons plus 6 neutrons. It has an atomic mass of 12.01, which is not exactly mass number, it's slightly different. And then we have atomic radius, which is generally measured in picometer, picometer, which is 70 picometer or 7 into 10 to the power negative 9 centimeter. The electronic configuration or how the electrons are placed in the shells, that is KLMN, is 2, 4. Now, we saw the synthesis of urea earlier, but this time we're just going to get a little deeper and look at the proper chemical reactions. Now, we know Frederick Wöhler carried out several reactions that resulted in the production of urea, which has a formula NH2CO, which is just NH2CO NH2, an organic component of urine. Sorry. One such reaction used lead cyanate and ammonia in aqueous solution. So we have lead cyanate with ammonia, not ammonium, ammonia with water, which gave us lead hydroxide and ammonium cyanate. So ammonium cyanate goes through a decomposition reaction. It decomposes to ammonia and cyanic acid. So we have ammonium cyanate NH4OCN, which gives ammonia and cyanic acid, which in turn is a reversible reaction to give us urea, as we call the compound NH2CONH2. Now, let's look at the types of covalent bonds. Now, we are not looking at single, double, or triple bonds. We are actually looking at polar, non-polar, and just look at coordinate bond also. So we have the polar covalent bond, which is ideally unequal sharing of electrons. Now let's say we have carbon dioxide. Oxygen could be here also, that's the general way of writing it. So if we look at the structure even more deeply, we have the crosses for carbon. So we have the dots for carbon, sorry, and the crosses for oxygen. Now we see that oxygen gets these electrons and carbon gets these electrons. Now oxygen is more electronegative. We look at the meaning of electronegativity a little later, but it just means that oxygen wants electrons a little bit more than carbon, so it pulls the electrons. Now, as a result of that, whenever we draw the structure of carbon dioxide, we draw it like this. Thing is, there is formation of partial charges represented by this delta symbol over here. Now let's look at non-polar covalent bonds. Now in non-polar covalent bonds, we have equal sharing of electrons. Example, carbon sharing electrons with carbon, nitrogen with nitrogen. It Carbon can form single, double, or triple bond with itself. Nitrogen and nitrogen form generally a triple bond to form N2. It could even be H2. In fact, even carbon and hydrogen has very less electronegativity difference. So we, and due to experimental research also, we kind of approximate it to be a non-polar covalent bond. Now we'll also look at coordinate bond, or it's also known as the dative bond. Now here, let's say we have carbon monoxide. Now carbon can form a double bond with oxygen. Anything more than that, oxygen would have one more shell. It does not want that. But carbon monoxide is actually stable. Yes, it's found on Earth. So basically it is stable. Now how will we do the structure of carbon monoxide? We cannot just put just a double bond. So here we tell that oxygen is forming a coordinate bond and it's sharing two electrons from the lone pair. To understand this a little better, let's draw the electron dot structure. And oxygen has these crosses. Now we see that oxygen and carbon get these electrons. So these form the bonded pair. Now we have oxygen has 6 electrons in the outermost shell. So there are these lone pairs. These lone pairs. Now these lone pairs are actually shared by oxygen alone. So here we can just say that oxygen is the coordinator and oxygen alone is coordinating the bond. That's why it's known as coordinate bond. Only one atom shares, there's no mutual sharing. It's almost like a half covalent bond. So let's just look at the location of carbon in the periodic table. So carbon is in the 14th column or group. The old representation was 3A, 4A, 5A, 6A, and so on. Now we represent it as 14. This is the new way of representing it. So carbon, this group is also known as carbon group. It consists of carbon, silicon, germanium, tin, lead. Yes, that group. Now, before getting into this, let's just look at the periodic table one more time. Now, this is not exactly that related to carbon, but can just stretch ourselves a bit, just for the just for fun, you know. So, from elements like from 100 and above, we actually have some names like UUT, UUP, UUS, UUO. Is it like the first part of all these elements, the name is the same, or is it like we have given the name so? Now, the thing is, this is like the older representation of some elements when we had not discovered them. So, IUPAC, which gave the nomenclature of organic compounds, also gave us the nomenclature of elements above 100, of above atomic number 100. Now, for them, we have some rules which we will look at. So, whenever we have to give the symbol, we will use one letter for one digit. Now, which letter is determined by the atomic number? So, let's say we have an atomic number 116. So, 1 we generally represent by U, so U, and then again U, and 6 we represent by hex or H. Yes. 116 was discovered and it was named Livermorium. Now we have to give, for 2 we would use B, 3T, 4Q, 5 pent, 6X, 7 sept. Now thing is, here for 7 we use sept, and in nomenclature of organic compounds we use H for hept basically. We wouldn't use H, we'd use hept. 8 for oct, and 9 we use E for N. N is nil. Nil we generally do use for 0. Un, like we use uno for 1, so un, u 1. So if we had to write atomic number 118, it would be just UUO. That would just be the symbol, but the name would be un oct, and we would add IUM. If we have another if we have another vowel, then we would just take out the normal the vowel and we add an I for am. Now we also did look at the fullerene family, that is Buckminster fullerene is a part of a family called the fullerene family. So let's look at how we define a fullerene and some more facts based on it. Then we look at Buckminster fullerene too in a little bit more detail. So fullerene is an allotrope of carbon whose molecule consists of carbon atoms connected by single and double bonds to form a closed or partially closed mesh with fused rings of 5 to 7 atoms. This may vary. The molecule may be a hollow sphere, ellipsoid, tube, or many other shapes and sizes. Now, graphene is an isolated atomic layer of graphite. Now, we have many layers of graphite. So, this is layer 1, and there could be a layer 2. Now, this one layer of graphite is called graphene, which is a flat mesh of regular hexagonal rings, become an extreme member of the family. So fullerenes with a closed mesh topology are informally denoted by their empirical formula Cn, where n is the number of carbon atoms. Hence, for some values of n, there may be more than one isomer. Yes. Now let's look at one member of the family which is very popular, Buckminster fullerene. So Buckminster fullerene is a type of fullerene with the formula C60. N is equal to 60. It has a cage-like fused ring structure. Just the technically you would call it truncated icosahedron that resembles a soccer ball made of 20 hexagons and 12 pentagons. Each carbon atom has 3 bonds. It is a black solid that dissolves in hydrocarbon solvents to produce a violet solution. The compound has received intense study, although few real-world applications have been found. Now, let's look at what are the chemical reactions we use to generally get to these fullerenes. So, graphite is on heating in the presence of inert gases gives a sooty material. Yes, on heating, generally we get a sooty material, which upon condensation gives the fullerenes. So from this, when we use a DC source, this is not AC, it's DC, and we put the graphite anode and cathode in the sooty residue in the presence of helium gas, we can get buckyballs. Now, some more about Buckminster fullerene is it contains 26 membered rings. Remember, we could get 5 to 7 membered rings in fullerenes. So this has 6 and 5, 26 membered rings and 12 5-membered rings. So 6-membered rings fuse with 6 of 5-membered rings. 5-membered rings will only be fused with 6-membered rings. It contains both single and double bonds with the bond distance, or the bond distance, will be 143.5 picometer and 138.3 picometer. Now we have looked at Buckminster fuel ring also. Now we are gonna look at structural isomerism. We did 4 types of structural isomerism. Now we look at another type of structural isomerism, which is tautomerism. Now, thing is, tautomerism is the phenomena where single chemical compound tends to exist in two or more interconvertible structures that are different in terms of the relative position of one atomic nucleus, which is generally the hydrogen. The true structures are called tautomers, and these type of isomer compounds usually differ only in the number of electrons or protons. They also exist in dynamic equilibrium. Now, this was in words. Now, let's put it into structures. Now, let's say we have as let's say we have two functional isomers. Let's say one is a ketone, or let's just represent it by keto. Another is having a double bond and an alcohol, so we'll represent it as enol. En comes from the double bond, and all is the suffix for alcohol. Now, this is the first type of tautomerism, and which is well, it's very important too. It's called keto-enol tautomerism. Now, in this tautomerism, which is this, which we have here, we can see this is the propanone, or the common name is acetone, and this we have the enol form. Now we see that, here that this is actually smaller, the arrow, and this is bigger. So what does this mean? So it is experimentally found out that the keto form generally dominates about 99.9%. It dominates, but we do have the enol form, and we have actually found that out through different chemical reactions. We'll not be getting into that now. So we also have the for phenols, the keto and enol form. Here the enol form is more stable, so the ketone form of the phenyl group is, it's not that stable as compared to phenol. Well, we have nitrosooxime and nitroacide. So one thing we have to note here is there are two conditions which we need to just check, so that if tautomerism is really possible. So they are: one is that we need alpha carbons. There should be at least one alpha carbon, one alpha hydrogen. So we have an alpha carbon. So the carbon that's attached to the functional group is called an alpha carbon, and then the hydrogen attached to that alpha carbon is called an alpha hydrogen. Now we also need an M or electronegative group that actually will pull the electrons. that will pull the electrons like sulfur, oxygen, nitrogen, etc. Now, what happens is in this case, let's see this. Now we have the alpha carbon, could be like this or like this. Those are one and the same structures. You can just flip them around. Now we have CH3. Now we have one alpha carbon, a hydrogen, which is attached to the alpha carbon. So that alpha hydrogen migrates because there'll be some partial bonds. They actually migrate and move towards the oxygen. So it forms OH. Now, so it forms only a single bond with this carbon, and now this is also giving a single bond, this single. It's not possible. So this loses a hydrogen, CH2, so it needs a double bond. Hence, the double bond is formed. Now, we did look at structural isomerism. We said that we would look at stereoisomerism a little later. So this is like the table of isomers. We looked at constitutional or structural isomers, which consists of 5 types. That is, we have the chain isomerism, then we have positional isomerism, functional isomerism, metamerism, and tautomerism, which we just now saw. Stereoisomerism is where there is difference in spacing between the carbon atoms or other atoms, which is this, they're called spatial isomers. Can be divided into enantiomers and diastereomers. Now, enantiomers is basically optical isomerism. Optical isomerism, in this type of isomerism, we have, it's actually that these two molecules are chiral, that is, when we see its mirror image, they are not congruent. That means it does not cannot impose itself on the other, like in this case. So if we put this over this, it would not, it would overlap. Yes. And then diastereomers can be divided into cis-trans isomerism, which is basically geometric isomerism, which it's cis-trans isomerism. We'll just look at it. So cis-trans, it always happens when there's a double bond. There needs to be a double bond. So cis isomerism is when they are on the same side, like the alkyl groups and hydrogens are on the same side. Trans isomerism, when they are on the opposite side, that hydrogen hydrogen, alkyl alkyl, they are on the opposite side. Conformers and rotamers are when we rotate it or there's a difference in the angle. This we'll not look at right now. There's one more thing we just note about enantiomers is that if we have, let's say, a cylinder here and we pass light, yes, light just pass through. Now we put a mesh kind of a structure and we close all of the other meshes. So basically we desire that we have one strip open, so we get light only in that direction, because light is an electromagnetic wave and it keeps oscillating, goes in different directions, so it's very random. So this light which passes out of this is known as plane polarized light, because we get only one strip of light. Yes. Now when this passes through the cylinder where we have the optically active compounds, we actually notice that this can turn the plane polarized light. They're optically active compounds. we call them for this reason. This is an experiment, and if we put another mesh like structure, this time if we have it a little tilted, light would pass through it. So just another interesting thing about enantiomers. Now, why do we need enantiomers? Now, actually, this has a lot of wide range applications. In fact, stereoisomerism, structural isomerism. In fact, we had a case many years back that we had R-thalidomide, which is a compound, and S-thalidomide. These both they're called enantiomers. So R-thalidomide is an antidepressant medicine and it's used for anxiety cases and etc. While S-thalidomide causes birth defects in pregnant women. Now what happened is they were actually mixed in equal quantities. So this caused 2000 birth defects. Now they knew about that kind of isomerism earlier. They or if they knew that these were enantiomers, they would have just checked the properties and understood it before putting it in the medicine, and there wouldn't have been any birth defects. So there are wide range of application in medicine and many other things. Now we looked at benzene. We said benzene is an aromatic compound, and we just said that we'll have to, these three are the right structures. These are the quantum model of benzene. That is, in quantum mechanics we have these lobes or the orbitals basically, which is the region where we can find the electron. It's based on probability. Now this is the view from one side, this is the view from another side. Now we saw these two structures. These both are the bond line structures. Now the question was, should we blindly follow it or is there a proper reason? Thing is, there is a proper reason for this. This reason is given by a theory called resonance. Now let's look at resonance. So we looked at the Lewis structure, the electron dot structure. It's very similar to the Lewis structure. So there are many organic molecules whose behavior cannot be explained by a single Lewis structure. An example is that of benzene. Its cyclic structure containing alternate single and double bonds shown is inadequate for explaining its characteristic properties. As for the above representation, benzene should exhibit two different bond lengths due to carbon single and double bonds. However, as determined experimentally, benzene has a uniform carbon-carbon bond distance of 139 picometer, a value intermediate between the carbon-carbon single and double bonds. Thing is, what they are trying to tell is that it was not a single bond or a double bond. In fact, it was in between. There was this partial bond. So it was an intermediate between the single and double bonds. Further, benzene cannot be represented equally well by the energetically identical structures 1 and 2. It cannot be represented by them. According to the resonance theory, the actual structure of benzene cannot be adequately represented by any of these structures we saw. Rather, it is a hybrid. It is a hybrid of the two structures called resonance structures. We just merge these structures and we get a very close resemblance to the hybrid. The resonance structures, the canonical structures, or contributing structures are hypothetical and individually do not represent any real molecule. They contribute to the actual structure in proportion to their stability. One more thing is about resonances. These compounds, they were thought to be had a particular stability. But the funny thing was, after they found out about resonance, before they found out about resonance and stuff, they realized that after doing experiments, it's actually more stable. Now, resonance also gives a proper explanation for that. So, let's look at benzene. We put this in brackets and we draw the resonance hybrid. It will be in between single and double, but it's uniform. So we represent it like this. This is the reason. Now let's look at ozone. Just some examples. Excuse me. Now, well, this is the structure of ozone. Yes. Now we can see double and single bonds. So what does this even mean? Shouldn't we just do the structure of ozone like this? Now this structure is wrong because the angle they found was too much for the two oxygens to have a single bond, these two oxygens. So that structure was anyways wrong. They actually found that ozone could have structures like this plus here, or else the double bond would be alternating and this would be a single bond. Now by finding the resonance hybrid, we did find something interesting. So we found that there were partial bonds. Partial bonds literally means partial charges. And this would actually be a proper plus, and you can put two partial charges, basically a proper charge. Now, before we get into anything else, we'll just look at, we saw that the quantum mechanic model of benzene was like this. So carbon has something, if we take one atom each and we put it, it would be like that. Now based on that, we actually put the electronic configuration based on the quantum model. So just so that we know about it, let's look at how we fill the electrons. Now, just one short note that we can note is that the s orbitals would always have two electrons. Two electrons. P orbital would always have 6 electrons. D orbital would always have 10 electrons. And F orbital would always have 14 electrons. So for carbon, we'd fill one s2. Now instead of going to P, we would go to 2s2. Then we go to 2p2. For hydrogen, it's just 1s1. Excuse me. Electronegativity, electronegativity. Well, what is this? So basically, we would define electronegativity as a qualitative measure of the ability of the atom in a chemical compound to attract shared electrons to itself. It is not a measurable quantity. Remember, it is not a measurable quantity. Well, it's defined relatively. It is not constant for an element, and it depends on the molecule and surroundings. It depends on many things. Then how do we give some convention? How do we actually just give some particular values into it? We use a convention given by Linus Pauling in 1932. Well, it's called the Pauling scale, but we'll actually look at it like what are the values. So he gave these values. Thing is, in some places we actually note hydrogen as 2.2 and carbon as 2.45 and some other values, but you can take it as this also, it wouldn't be a problem. It's like what we have to note here is that the electronegativity difference between hydrogen and carbon is not as much as carbon and oxygen. Carbon and nitrogen is, this is not, it may vary, so it will be a little bit more the difference. So we see that the hydrogen carbon has very less electronegativity difference. So more the electronegativity difference, more polar covalent bond character. That is how it basically works. Now one more thing about polar covalent bonds is that it basically has an ionic plus covalent character. Let's take an example. Let's take HCl. It is a covalent compound. It is not ionic. Now, this is one of the proofs that hydrogen is a non-metal. It's not a metal. But how can we just say it dissociates in water? Yes, to form ions. Now, the thing is, hydrogen chloride or HCl has a lower melting and boiling point than the ionic compounds. And then there are some other things, the hydrogen, chlorine, and chlorine is a non-metal. So if hydrogen is a metal, then it'll be ionic. If it's not a metal, be not be ionic. So then we had to do some experiments and find out. And then we also looked at some other things like, is it like, we looked at the melting point, boiling point, hardness, a lot of other things. And then we found that the HCl is covalent. It's polar covalent because hydrogen and chlorine, see, chlorine has 3 electronegativity, which is an approximate value. Hydrogen is 2.1. Basically 1. That's a lot. So that means it's a polar covalent compound. Now the interesting thing about HCl is when we put it in water, let's just draw the structure of HCl, the electron dot structure. It would be like this, Cl, like this. Now, chlorine pulls the electrons more towards itself. So when we have water coming in, it splits HCl. Now the thing is, how does it form H plus and Cl minus? The electron goes. Now the thing is, it's more towards chlorine. So if a force comes, electrons are more towards chlorine. So if the force comes, it go towards chlorine again. So it would just have Cl minus and H plus. The thing about HCl, and it's the same for water too. So thank you guys. Hope you guys enjoyed the live session. If you did, do hit that like button, subscribe to the channel, and share it with your